Good morning, my dear student, and welcome to my channel, that is Easy Chemistry by SBG. Today we will see the isomerism in coordination complexes. Isomers are defined as the complexes having same chemical formula but having the different structural arrangement. Complexes having same chemical formula but having different structural arrangement. Different structural arrangements, and the phenomenon is known as isomerism, and the phenomenon is known as isomerism. So there are main two type of the isomerism of the coordination complexes. Structural isomerism and stereoisomerism. Structural isomerism arises due to the difference in the structures of the coordination compounds. First is ionization isomerism. Here is a difference in the ions between the two isomers. Second is hydration isomerism. There is a difference in the water molecule. Then third is linkage isomerism. Then fourth is coordination isomerism. In stereoisomerism, there are two types again: geometrical isomerism. Geometrical isomerism, one is a cis and second is a trans isomer. And optical isomerism, one is a D and second is a L. D stand for dextrorotatory and L stand for the levorotatory. We will see it in detail. Now see first ionization isomerism in detail. Ionization isomerism occurs because of the change in the ions. If two coordination compounds which differ in the distribution of ions between those directly coordinated and the counter ion present in the crystal structure are called ionization isomerism. For example, if we see these two compounds, we see the molecular formula of this compound CO NH3 5 times bromide, and counter ion is sulfate, while in second same central metal cobalt NH3 5 times SO4 and counter ion is a bromide here. Now these two complexes, if we dissolve it in the solvent, then they gives the complex ion and sulfate. First, this first complex in solvent gives counter ion as a cobalt NH3 5 times bromide 2 plus SO4 2 minus, it's a counter ion, and the second compound, after dissolving it in the solvent, it gives the same counter ion like the cobalt NH3 5 times SO4 plus bromide ion. Now what is the difference between these two? The counter ion is different. If we take the test for the barium chloride, if we add the barium chloride solution, then first complex gives the precipitate of barium sulfate. If we add the barium chloride, then there is a formation of the barium sulfate precipitate for the first compound. But for the second compound, if we treat the second compound for the barium chloride, then there is no formation of the precipitate. This chemical test suggests that there are two different isomers of the same compound. This can be further supported by AgNO3 test. If we take the AgNO3 test, then AgNO3 test will be the silent for the first compound, but for the second compound, if we treat this with the AgNO3, then there will be the formation of AgBr precipitate. Now this test suggests that there is a presence of isomer and ionization isomerism is there. We can write the number of example for the same. We see the another example for the ionization isomerism. Then chromium NH3 5 times, NO3 SO4, and same molecular formula CrNH3 5 times SO4 NO3. See the ionization isomer after the dissolution in solvent, it will give the sulfate ion and complex ion, that is chromium NH3 5 times NO3, while the second complex after dissolving in solvent, it gives a different ion in the solution, chromium NH3 5 times SO4 N plus SO4 plus NO3 minus plus here 2 plus. So this is an example of the ionization isomerism. Second more example of ionization isomerism is platinum H2O5, chlorine, bromide is a counter ion, and same metal platinum H2O5, bromide, and chlorine is a counter ion here. So these are the example of the ionization isomerism. So the second is hydrate isomerism. Second structural isomerism is hydrate isomerism. Now the compounds formed from the same complex molecule with the same number of water molecules, which can present either as a water of crystallization or attached to the central metal ion wholly or partly, are called as hydrate isomerism. The best known example of this hydrate isomerism is chromium H2O6 times Cl3. This same formula, we can write the number of isomers as chromium H2O5 times chloride and Cl2 and one H2O molecule here, and second Cr H2O4 times Cl2 Cl and H2, twice H2O here. One more isomer we can write for this, chromium H2O 3 times Cl3 and thrice H2O. Now see, the water molecule is different. The number of water molecule here, the 6 water molecules are all coordinately bonded to the central metal ion directly, while here in second isomer the water molecule is outside the square bracket, and in next formula the two water molecule is outside the bracket. Such isomers are called as hydrate isomerism. Hydrate isomers. Hydrate isomers, and this phenomenon is called as a hydrate isomerism. Next type of the isomerism is linkage isomerism. Linkage isomerism, some ligands coordinate to the central metal atom or ion through one type of donor atom in one complex and through the another type of the donor atom in another complex. These two structures are called as the linkage isomerism. As we know that the ambidentate ligand ambidentate ligand has the more than one donor site of that ligand, more than one donor site. If the ligand having the more than one donor site, then they can show the linkage isomerism. Now see in above example, the nitro group, NO2 group, here it is bonded to the central metal atom through the nitrogen, while in second structure the nitro, it is bonded to the central metal atom through the oxygen. So we can name it as a nitrito, but the formula is same, NO2. Such isomers are called as a linkage isomerism. Here nitro behave as a ambidentate ligand, hence in one case the linkage of it is through the nitrogen, while in the another it is through the oxygen atom. There is difference in the linkage with the same central metal ion, that is cobalt, and oxidation state of cobalt is 3 here, results into the formation of two different isomer of the formula. Here we can write the formula of these two isomers as a cobalt NH3 5 ONO 2 plus, and for the first cobalt NH3 5 NO2 2 plus. These are the formula of these two isomers. We can write the example for number of example for the linkage isomerism. Number more examples for the linkage isomerisms are chromium H2O5 thiocyanide 2 plus and its isomer chromium H2O5 isothiocyanate. So thiocyanide and isothiocyanide, these are the isomerism. Then second more example is cobalt NH35 SO3 plus and sulfate CO NH3 5 SO2S plus charge. These are the linkage isomerism. Linkage isomers. Linkage isomers means the same molecular formula, but the linked atom is different. Now see the next type of the structural isomerism is ligand isomerism. Ligand isomerism is a type of structural isomerism in coordination complexes which arises from the presence of ligands which can adopt different isomeric form. For example, this is trimethylene diamine. Trimethylene diamine, and we can write it in short as a TN, or 1,3-diaminopropane, or 1,3-diaminopropane, and its isomer is propylene diamine. Propylene diamine, and in short we can write it as a PN, or the IUPAC name of the same is 1,2-diaminopropane. 1,2-diaminopropane. Now these two are the isomer, these are the ligands, they itself behave as an isomer. If these ligands are attached to the central metal atom or ion, then they behave as a isomeric complexes. We can write the formula for the same. For example, see, cobalt, Pn stand for the propylene diamine, cobalt, Pn twice, Cl2 chloride, and its isomer is cobalt, Tn twice, Tn stand for trimethylene diamine, Tn2 Cl2 chloride. Now see, this Pn and Tn, they itself isomer of each other, and they are the ligand, and that's why they are the ligand isomer. So we can write the formula for the structural formula for the same. So it is likewise NH2 CH2 CH CH3 and NH2 here, other two chloride, and one more Pn, that is propylene diamine structure, NH2 here, CH2 CH and CH3. Second structural formula for the second isomer, it is also under 6 coordination number of cobalt is a 6, NH2 CH2 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 and NH2 here, other two chlorides, and one more Tn, CH2 NH2 CH2 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 and NH2. The oxidation state of the cobalt is +3 here. So these are the two isomers. The ligands are different. Ligand themselves behave as a isomer. See, they are the isomer, and that's why these two complexes are called as a ligand isomer. Ligand isomers. Now, next type of the isomerism is coordination position isomerism. Coordination position isomerism. In this form of the isomerism, the distribution of ligands between the two coordination centers differ. Usually in polynuclear complexes. Polynuclear complexes means more than two central metal atom or ions are there. So in polynuclear complexes, the position of the ligands is or the result into the two different arrangement as shown here. Now in first isomer, the distribution of ligand is unsymmetric. If we see, the 4 amine group is here, and here is a 2 amine. Instead of 4, there is a 2 amine group and 2 chloride attached to the second cobalt, while in second it is an symmetric. In second it is symmetrical arrangement, and here unsymmetrical arrangement of the ligand. So in second, the exchange of one of the ammonia group with one chloride ion from the another central metal ion gives more symmetrical arrangement. So this symmetrical arrangement by exchanging the chloride, if this chloride is goes to this cobalt and one ammonia is go to this cobalt, then there will be the symmetrical 3 ammonia here, 3 ammonia here, 1 chloride, 1 chloride. So such a arrangement, symmetric or asymmetric arrangement, the position of the bridging group remains unchanged in both the cases, and such a isomer is called as coordination position isomerism, and it is exists mainly in the bridging ligand or in the polynuclear complexes. Number of example we can write on the same. For example, the next example. Fe, NH2, it is bridged, and O2 is also here. So NH3 3 times chloride, and here is also NH3 3 times and chloride. This is a symmetric arrangement of ligand. We call it as a symmetrical isomer, and its isomer we can write as a asymmetric Fe. Bridging ligand as it is we have to write. Then Fe here NH3 2 times Cl2, and here NH3 4 times. Now this is an isomer. Now the coordination position is different, and that's why it is called as coordination position isomers. Coordination position isomers, because the position of the coordinated group is different here, and that's why it is called as coordination position isomers. Next is a polymerization isomer. Polymerization isomers, these are not isomers but were classified as the isomers by Werner. Complexes having the different molecular formula but the same empirical formula are called the polymerization isomers. Means the empirical formula between the complexes is same. If we see the example, platinum diamine here, this example, and his again. Now if we try to write the empirical formula of these, then the empirical formula of both the complexes are same. If we see the another example, cobalt NH3 thrice, then NO2 thrice, this is an complex. Second, CO NH3 6 times, then CO NO2 6 times. If we write the one more example, then cobalt NH3 4 times, NO2 twice, second CO NH3 twice, and NO2 4 times. Now see these examples having the same metal cobalt, then linked group, that is the ligands are also same, ammonia and nitro groups are coordinately bonded to the central metal atom, that is cobalt. If you write the isomer, these are the isomer, the empirical formula same, and the empirical formula is same because cobalt NH3 thrice and NO2 thrice. This is an empirical formula. If we see the second example, then here N into empirical formula, N into empirical formula, here N is equal to 2 and here the N is equal to 3, N is equal to 3. So these are the polymerization isomer because empirical formula is the same but the linkage or the molecular mass is different, and that's why it is called as polymerization isomerism. The use of the term polymerization isomer for these complexes is unfortunate, as a polymerization refer to the formation of the compounds by the repetition of the same unit, which is not the case here but difficult in the determination of molecular weights of the complexes. These complexes were however classified as a polymerization isomer. So these are the structural type of the structural isomerism. In next lecture we will see the stereo isomerism and then we will solve some MCQs on the same topic. Thank you. If you like my video, then please share, subscribe and press the bell icon so whenever I add the new videos you will get the notification. Thank you.